Okay, I apologize. I had to check on something there. Checking my phone. So, like I said, if we get a positive deflection in AVF, it's going to be moving, the direction that the electricity is moving down. So if we add those up, what happens if we put two forces together? And one of them is moving down, the other one is moving this way. We know from physics, and like vectors, like high school physics, this is like high school physics. If we push something, when something is like traveling down a stream, if we're trying to push it to the opposite shore, it's not going to go straight to the opposite shore, is it? It's going to be pushed kind of in a gradual line towards a diagonal path, right? So if we sum up these two forces, it's going to go down that way. So that's why you can tell our axis deviation from those two leads. And the way that you check that is you look at the AVL, and if it's going perpendicular to that, if it's isoelectric, that is. So we've got, if we're looking at AVL, which is from the midpoint between lead 2 to the SA node, if we're looking at that, at the heart, half of our electricity is going to be moving this way, and half of our electricity is going to be moving down to get to the ventricles, right? So that's how we know each of the respective portions of the axis. So the really key to understanding this kind of axis thing and all that is to understand the leads. And the way to do that is draw out this triangle, all right? And a good way to remember it is I always go, I'm right-handed, so I go 1 is always on top. And then I go 2, and then 3, save the best for last because I'm right-handed and my favorite number is 3. So 3's on the right-hand side because it's right, because I'm always right, right? Not really, rarely. Rarely, am I right? So that's a good way to remember that. And you should probably like draw this out like a dozen times so that you know how to draw it out. And the first thing you should do on your test, draw out this triangle in each of the leads and label them. Because if you can remember that, you can solve a lot of problems with the cardiac tissue and its electricity, as if you know the leads. All right? So the good way to remember the computed leads is to go off of what they mean. All right? So AVR means I'm looking towards the right. That's literally the reason why it's named AVR. It's looking from the lower left-hand side, like down by your hip, up to your right shoulder. Our AVL is looking from our lower right hip up to our left-hand shoulder. And then our AVF is looking from straight down from our head to our feet. And that's why it's F. It's because it's foot. Our positive pole is our foot. All right. So that's that. And a good way to check it is check the isoelectric lead. Which one is it? If it's going both ways, that means it's propagating both ways. All right. And that means you're correct in assuming that that is your axis. All right. So an axis just means what way the electricity is moving through the heart. All right. Now, we're going to get a little bit, I don't know how far we're going to get into this because I feel like, God, I don't know how much they can expect us to know. Like, do they want us to read an entire fucking 12 lead on this test? Because if they do, goddamn, they're crazy. That took me a long time. I was an EKG tech, and I like sat there and read the book on the thing for weeks until I finally understood everything. But it might be worth noting some of the basics. So like, she talked about figuring the rate today. The easiest way to figure the rate is to find one of your R complexes of your QRS complex, find one of your R waves, which is the upward deflection, find one that's close to a heavy dotted line. So there's going to be like 4 small lines in between each of these things, and they're going to make up a box. And those correspond to like time measurements. You don't need to know that if you know this method right here. So if we find one on a heavy line or close to a heavy line, we can use these boxes to count specific numbers that'll give us our rate. So if we find one on the line, we say the first line 300, then we go 150, or the first line after, excuse me, I wrote this down and then I didn't move the line, or move the numbers. So we go 300, and then 150, and then 100, 300, 150, 100, 75, the next line would be 60, and then we go down to 50. So these are the numbers that you've just got to memorize. The way we get these is from division of each of the lines. Each line is like 0.4 seconds, and each big line is 0.04 seconds, and then each between each of these heavy lines is 0.2 seconds. That's not the way you should remember it, okay? This is by far the easiest way to figure out if or what the rate is, or get pretty close, is if you go from counting these lines. So wherever the R complex is, or R line is, we're going to count 300, 150, 100. Where's our next R complex? It lands right on this line. So what's our heart rate? 100. Simple enough, right? So just memorize these numbers. 300, 150, 100, 75, 60, 50. There are 6 numbers, and I promise you they will make your life so much easier than going through and dividing all these small boxes and how many complexes fall in each of them. It'll just make your life much simpler than doing all that calculations to just count this way and figure out the approximate rate. Now, if we don't have one close to this, or say one falls in the middle of it, like say we got like a line right there, well, that's fine. We just know our rate somewhere between 75 and 60, and we can get pretty close. And a normal heart rate we know is between 60 and 100. All right. So if she's going to ask, is this like bradycardic? Is this tachycardic? Anything over 100 is considered tachycardic. Anything below 60 is considered bradycardic. Just slow or fast. And this is the way you can solve that problem, is if she gives you a rhythm strip. You can count the lines, 300, 150, 100, 75, 60, 50, and that'll get you in the ballpark. And like she said, that's why she said she's not going to put 2 numbers really close, because we're not going to have to figure exact. We just need to get to the point where we kind of know if it's fast or slow, and we know if it's within normal range. All right. So that's that. All right. So this is where things get really complicated. We are learning how to interpret EKG. So if you just wanted this day's lectures, you can stop now. But I have a feeling that when we get to this lab, they're going to be teaching us how to do interpretation for arrhythmias and for blocks, whether it be in the AV node or the bundle branches, and also reading for MIs, which is 3 big things that are kind of hard to get the hang of. But our first step in interpreting any EKG is always going to be determining the rate. And if they ever give you a 12 lead, that's like all 12 leads printed out, always look for the rate in lead number 2. That's going to be the one that's easiest to pick out how fast the heart is going, because they're usually going to put it down towards the bottom. They're going to put it on the second line, and they're going to give it the whole sheet, so you can actually look through all the complexes and figure out heart rate. Then you're also going to interpret the rhythm. So our rate is going to give us clues. How fast our heart is going is going to give us clues about our rhythm. And then we're also going to determine its regularity. So regularity is just a judge, it's just an eyeball of looking at the R complexes and seeing if the space between each of them is consistent as we go along. So if we had an RR interval like this, and then all of a sudden it went like this, that is not a regular rhythm, because our R interval went from this is something like this, so much longer. All right, so that's an irregular rhythm. All right, so our specific rhythms we'll have to learn in the lab, and I'll make another video to help with that. But it's suffice to know right now that a normal heart rhythm is called normal sinus rhythm. And it's called sinus because it's coming from the sinoatrial node. That's our main conductor in this whole shit show we call the heart. So we named it after it. Normal sinus rhythm, and it is always going to be somewhere between 60 and 100. Sometimes it can go faster, sometimes it can go a little slower. We call that sinus bradycardia or sinus tachycardia. We'll learn about that soon. We can also have things called ectopic foci controlling our rhythm instead of our normal SA node. So if our SA node is injured in some way, those nodal cells in it are injured some way, we can get some of these ectopic foci or ectopic pacemakers to pick up conducting our whole system. And when it does that, it creates an arrhythmia. So we can have our AV node that can start conducting the show. We can have ectopic foci or nodal cells in some of our ventricles do it. We can have some of them in our atria do it. And if we get a bunch of them, we can get like atrial fibrillation. If we have a bunch of different ones in the ventricles firing off, we can get ventricular fibrillation, which is lethal, by the way. It just depends on where the signals are coming from. And if you understand where the heart, where each of the leads are measuring from, and which way the lines are going to be moving for which way the electricity is going to be moving, it makes it much easier to understand arrhythmias. And if you understand the normal pattern of electricity in the heart, it makes understanding arrhythmias also much, much easier. All right. So, debating whether to go into it now or not. I think I'll just save AV node blocks and bundle branch blocks and MIs and that kind of stuff for another video here on like Tuesday when we have that lab, and then we'll just call it good on this one right now. I hope this clears something up for somebody. If it doesn't, if it does just one person, that'll be worth it, but if not, thanks for watching, guys.